When people vote, the biggest challenge for those running the election is to prove that the candidates who lost actually lost. In paper-based elections worldwide, a process has been in place for 150 years so that those concerned about the conduct of the election can really see what's going on and be satisfied with the results. As populations have grown and as other government paper processes have been automated with computers, electronic voting has been created.
You have chosen Susan.
This has led to many improvements in elections. For example, computers can help people who cannot read to mark the ballot. Votes collected with computers can be counted electronically.
Susan wins.
However, this has created new risks. Actually proving to Jamie that he did not win becomes very difficult because the votes are not on paper. Casting a paper vote is very simple. It's obvious the vote has made it into the box. Casting an electronic vote with the same level of safety as the paper vote has been described as the hardest transaction to automate in all of computer science. The electronic vote must be protected for transport so that it cannot be read or changed, and it must be impossible to connect the voter with this vote. And like the security of the ballot box padlock, it must be possible to prove that the vote is secret, safe, and private. Unfortunately, because we're attempting so many things together, electronic voting is most susceptible to system bugs, failures, and malfeasance at this particular point. So in order to prove to Jamie that he definitely did not win, some electronic voting systems have had to reintroduce the election steps of the paper system. For example, some voting computers send the vote electronically, but also print out a paper copy. This is a form of verification because the voter has something meaningful to check. If the paper copy is wrong, she can see it and alert others. This also reintroduces some of the constraints of paper voting, namely that you need to be able to read to confirm the printout is the same as the screen. And this printed ballot cannot be taken away by the voter as a receipt. It must stay at the polling place because the voter's vote must remain secret from others. To prove to Jamie that the computers have done the right thing, some of the computers are chosen for an audit and the printouts are hand counted to confirm they match totals reported by that computer. Unfortunately, this means elections now run both paper and electronic processes, and that makes everything even more complex. It would be better if the system could all be electronic, but with convincing proof that the computer has operated correctly. This is where COASCA comes in. COASCA is a voting system that changes the way electronic votes are cast, so that capture of votes is simpler and safer, and can be more easily proven to the voter without having to do both paper and electronic ballots. COASCA does use some paper receipts for verification, but they can be optionally discarded by the voter. COASCA creates a temporary list of the election candidate names in a shuffled order. This order is different for each voter, and only the voter sees this order. The voting computer reads this order. From here on, we will show you voting in ranked order, since COASCA works with all ballot styles. Notice we give Susan our top ranking of 1. The computer prints out a voting receipt. The receipt is the voter's choices, but in the shuffled order. Even though the voter saw the official ballot order on screen, here they verify that their vote is correct, even with a list of shuffled names. The list of names is destroyed so it remains a secret. The printed receipt can be taken home by the voter. Missing the shuffled names, the receipt does not reveal to anyone else how the voter actually voted. A code on the receipt allows the electoral authority to reorder the receipt back to the legal ballot order, which then reveals the vote for counting. A copy of the receipt is taken by the computer and sent to the central system. However, this time, the networks are not carrying votes, just receipts. Our voter can go home and look up her receipt to confirm that it is among those on the central system. She can also examine the receipt, which is signed, to confirm it has been recorded by the electoral authority. At the end of the election, observers and the election authority provide devices that cooperate to reveal the shuffled orders allowing the reordering of those receipts back to countable votes. How does COASCA actually show that all the votes got recorded as the voters wanted, and that all the recorded votes got processed and included in the count without any votes changing? Let's vote, this time with some trouble thrown in. We'll see how it's impossible for loss or damage to occur undetected. The list of shuffled candidate names, which is how COASCA protects the final vote, can be examined to confirm that it's an official list. This is similar to the way paper ballots are securely printed and checked before an election. These lists are made well before the election. A selection of them is audited to make sure the shuffled order can be undone correctly, back to the legal order. It's also not possible for this voting system to create more electronic ballots during the election than those that were made in advance of the election. The list of shuffled candidate names can be audited by the voter in case the voter does not believe that the displayed order of the candidates is correct, or that the order in the QR code may be different. However, the challenge list cannot now be used to vote, because its order is no longer a secret. So the voter gets another list, and can vote with it, or challenge that list as well. This can be repeated as many times as the voter wants. Finally, the voter is confident that the ballots are correct. The voting receipt can be electronically examined to confirm it has been centrally recorded by the electoral authority as cast. All the receipts can be observed on the network. They can be observed at the central location. No one can see the actual votes. No encryption of the network is needed because the receipts already protect the votes. In fact, the central location is just a public website. All the receipts are made public. A day's set of receipts is signed as a batch. Voters, and anyone, can look up individual receipts in a batch. The voter can compare this to her printed receipt to confirm her vote is unchanged and remains among those collected. Voters checking are very likely to find any lost or damaged receipts. After the close of the election, independent key holders convene. Each has a key they made for themselves and a key they gave us to make the blank ballots. Only by coming together can they process the receipts back into votes that we can count. Here we pick a receipt at random. These are the secret positions which give the correct location of the candidate names. When we go and get these for all receipts, then we shuffle the batch so the votes we decrypt can't be linked back to the receipts. If you voted first on this system, we don't want your vote to be decrypted first, or this would put your privacy at risk. Once again, we're going to illustrate the vote as a preference order rather than a simple X. This way you can see how the whole ballot is protected, not just the single mark the voter makes. So let's say the voter provided a vote with 4 choices. This is the receipt they would have. We will reorder these pairs to the natural order, and we are done with the receipt. This is all we need to get back the voted list. Now we recover the legal order of the shuffled list. We show how math is the key to this, but in the following examples we are using only very small numbers. In a real election, these numbers are almost 100 digits long. Each of the key holders performs their part of the decryption. They do it like this. We take the first secret position. Our key holder uses their private key, which is just a number they know. We take the public key, which did the encryption. The first key holder does this calculation. We need all 3 key holders. The other 2 key holders do the same with their keys. So we have 3 values, 41, 16, and 21. Now we combine them. That's our combined decryption. Now we get the secret and use it. So this is candidate number 2, which is Susan. She gets the voter's first preference. The key holders repeat the maths the same way to get the rest of the ballot, which is 2, 1, 4, 3, back into legal order. And there's the vote we can count. This is done for all the receipts. They are hand counted, or the vote data are machine counted. But how does Jamie know that the key holders did the right thing with each math operation? Each key holder has to emit a proof at each stage. Since decryption is just maths, we can actually prove some of the details of the steps they used to show that it was done right, without giving away the private keys the key holders have. Why don't they just hand over the private keys so you and I can do our own decryption? The answer is that decryption must happen under conditions where the keys cannot be used to align any one receipt with its vote. If anyone had the keys after the election, they could go back and work out what your vote was from your receipt. So instead, we're going to make the key holders give us some of their workings, just enough to show that they did the right thing. To show you how this is possible, here is an example of how this works. Imagine that you're a teacher in a classroom and each student has a word puzzle like this. You've promised that the first student who can find all the animal names will win a prize. You don't say how many there are. The problem this creates is, how can you know whether a student has found all the animal names? One student may say they've found them, but in fact be missing one. Another may include words that aren't animals. What you need is a quick way to know who has done the puzzle without the student having to call out the animal names or where they are on the board, since this would tip off the other students. Here's how you can do this. Students who say they have done the puzzle should add up the consonants and vowels in their found animal names. Students who've missed words will have too few. Students who have extra words will have too many. So to check that the votes were calculated right, we check some information the key holders emit when they do their decryptions, like the vowels and the consonants. Each key holder emits 7 numbers when they decrypt in our setup. We can know right away if the calculation you saw before, resulting in the first preference for Susan, was done right or not. We can know this without also needing any private keys or having to redo the decryption ourselves. The math the key holder does creates this first public proof number. To make the third number, he uses a random number. He rolls the dice. The key holder can publish these 7 numbers. That's the proof for this key holder's work on the ballot position. The key holder has told us about the answer without giving away the secret they used to get it. Jamie will now check that it is indeed plausible. He can check 2 products, which can only be correct if key holder 1 did the math exactly right. We take our original public key, which is 16. 35 equals 35, so this check is right. 41 equals 41, so this check is right. So this proves this key holder arrived at the published products 35 and 41 by performing the math behind them correctly. Jamie can perform this math on all the ballots if he wants. Maybe you don't understand all the math in this animation, but we hope you can see that it is only math, multiplication and addition, that Kowaska uses to give you extremely strong proof that all is well and figures don't lie.
All of the proofs described in this animation are made public along with the receipts and the final votes. Anyone can use their own tools or tools from the internet to check the calculations performed in the election. It's not possible for votes to be damaged, lost, or changed without these calculations also failing. Kowaska is an international provider of verified electronic voting systems. All are free open source software.